welcome to the stream processing at scale with Spring XD and Kafka. When I initially submitted a talk, it was really meant to be Spring XD and as much as we can get with Spring XD. But afterwards, as you will see, how many of you have attended the Spring Cloud stream and Spring Cloud data flow sessions, right? How many of you have attended the keynote? It was the dinner, so you should have been there. But so yeah, I mean, there is much more to this story. It ties pretty well together. It's basically a tale of an evolving project that I'm very excited to be part of. My name is Marius Bogoevici. I'm a staff engineer with Pivotal. I'm working on the Spring XD team and basically its successor projects, mainly Spring Cloud Stream, but also a little bit on Spring Cloud Data Flow. Also, Spring Integration, and mainly Spring Integration Kafka. So I'm particularly proud of this, to deliver this talk because it's a lot of stuff that I've been working on. So it's good to show. And the only point I'm trying to make is that I have, apart from that, I have a deep ingrained love for open source, having worked in there at Spring Source before and at Red Hat and JBoss. So I strongly believe that there is a lot of good value. I'm sorry. Thank you. Better? Okay. Don't do it yourself, don't try it at home. It's never get done. Okay, so. Yeah, they had us put this slide in because a lot of stuff that you will see right now is very new, very cutting edge. So basically, you will see actually a lot of work that's under development. So we don't have definite timelines for it, but we're working really hard to get a release on everything. And what I'd like to start first is how would you define stream processing? How would you categorize a stream processing application? Because that's the main focus of our talk, beyond Kafka, at a more abstract level. If anyone would. Anything that's continuously consuming data. George. Yeah. Essentially, the story is that in what's being perceived as the big data landscape, and big data is quite a loaded word right now. It's kind of abandoned. But everything that deals with processing large quantities of data, there's been a shift in the technologies and in the application requirements. So what typically was the domain of batch processing, collecting large amounts of data, processing them, and so on and so forth, has basically started getting more stringent requirements for real-time processing. So we don't want to basically be able to find out that something happened the next day. We want to see it as it happens. And we have the capability, we have the technology, we have fast networks, we have fast processors, we have memory has become a commodity. So basically, that's kind of a new topic here. The other, some characteristics of stream processing applications are beyond high volume and low latency, but also it's not only about, let's say, data, like series of disparate events that happen, right? I'm collecting, for example, the logs of an application. So all the entries are related. They happen in a certain order. They have to be processed in a certain order. I have to be able to process a group of data as it arrives. So This adds some additional demands, for example, for partitioning, for example, in a concurrent scenario. Some examples are the famous Internet of Things, things like fraud detection, measuring quality, so log aggregation, predictive maintenance, like the example that you saw last night was a pretty good one, like detecting when a truck fails. We want to be able to detect that and be able to react and point them to the nearest service center. So that is basically kind of that's the type of problem that we are trying to solve, and this is the type of problem that we're looking at. So let's put together our toolkit. And the first thing that we're going to look at is Kafka. How many of you are using Kafka currently? Very good. How many of you are planning to migrate to Kafka? A lot. Good. So together, how many of you are just interested in, so what makes you, for example, what makes you interested in Kafka? The first thing that comes to mind. Why would you want to migrate to Kafka from other messaging systems? I'm sorry? Right. So persistence is one thing. Other reasons. Speed. Event sourcing. Right. So I won't dwell too much into Kafka as itself, because tomorrow morning there is an in-depth presentation about Kafka itself. It's going to be delivered by one of the PMC members for Apache Kafka, so he's going to go into a lot of details. Joe Stein, I strongly recommend to go. I think it's at 10:30. What I'm going to try to do is just rehash a few points about Kafka and talk a little bit about things that are relevant to us from a stream processing perspective. So of course, Apache Kafka is a high-throughput distributing messaging system. It started at LinkedIn, but it's been open sourced in 2011. They describe themselves as publish subscribe messaging they thought as a message log. And that's referring especially to the implementation of the middleware itself. It describes itself as one of the goals is to decouple the data pipelines between producers and consumers. And while that can be said about each and every messaging system to some extent, in the case of Kafka is the publish-subscribe nature of the interaction that adds a little bit to this decoupling. So everything in Kafka is essentially stored in topics. And topics themselves are divided in partitions. Partitions which are read and written independently. So that allows a producer and a consumer to actually access that data at a different pace. A producer will always write at the end of a partition. A consumer will read data sequentially as it comes in. And that also explains that also accounts for the high performance of Kafka, because reads and writes are linear. It basically, it's a very interesting application of the nature of storage, that linear and reads and writes are very, very performant, and very often it's actually, they don't even happen on the disk. So it relies a lot, for example, on the page caching that the operating system does. This allows essentially to have data read and written very, very fast. Not only that it's basically partitioned, and not only that it's relying on linear reads and writes, but these partitions are it's also a distributed system. So it provides failover to replication across a cluster of brokers. So for example, you have here, like in this diagram, you have an example of two partitions of a topic, which are essentially replicated across 3 brokers. So for example, partition 0 is replicated on broker 1, broker 2, and so on and so forth. Now, this replication is not only relevant for, let's say, obviously for failover, but it also accounts for another aspect of Kafka's performance. Producers writing to different partitions end up very often writing to different brokers. Again, this type of partitioning is very beneficial for overcoming the limitations of the network. So it's very easy, for example, to saturate the interface of a broker when everyone's writing to the same node. Writing to different nodes basically allows to distribute that load. And that's another thing. And of course, it relies on Zookeeper for state management. In summary, why Kafka for stream processing? Why do we like it? Well, obviously, the high throughput, low latency are a reason. It provides high performance on what is more or less commodity hardware. So we can get very good rates even using magnetic disks, right? Which allows for persistence, allows for storing basically large amounts of data. One aspect of this is that because of its log structure and because of its long-term persistence, which was actually brought up, it allows replayability. So normally, like with most messaging systems, even in a publish-subscribe scenario, you will receive messages, right, for the duration of your session or maybe a little bit back. But with Kafka, you can actually replay historical data from very early on, if, of course, there is enough space to store that much data. So that's actually it makes it very useful for being used as a master data set. And there is a school of thought that thinks that, for example, replaying a Kafka topic is a good replacement for batch processing in a way. Consumers are completely independent from each other. So it's not only because the interaction model is not based on the brokers pushing data to the consumers, but the consumers actually requesting data from the brokers. They can really evolve, like if you have, for example, multiple consumers, and by that I mean multiple applications consuming data at the same time, it really allows each of them to receive and process data at a pace that actually suits them. It allows concurrent reading, so you can have, for example, multiple consumers, right? An application can actually have multiple nodes, which are part of that application, reading off the same topic. In case in which, for example, partitions will be divided across the nodes. And one of the consequences of the linear reads and writes that happen within Kafka is that it guarantees order delivery within a partition. So the messages that arrive to a partition will be delivered exactly in the order that they have been written. Again, that's very important if you think of the aspect that I mentioned earlier, that we really want to see an application events in the order that they happen. Really want to see history as it happens, and Kafka makes that possible. Conversely, there are certain scenarios where Kafka is not that suitable, most notably competing consumers. So it's very hard to implement a scenario where two consumers listening to the same partition on the same topic will not receive the same message. But that's not something that you really should be concerned about when you're looking at stream processing. Stream processing mostly deals with really streaming data sequentially between nodes, and Kafka is very good at that. That's basically Kafka. What's next? Well, a question?
When you say stream processing, does that imply single-threaded? The reason I'm asking is, typically, you have any kind of queuing system with multiple consumers on it.
Right.
You get throughput, right? They're going to process out of order. Probably. Even though they receive the messages in order, you're not guaranteed that they'll be processed.
That is correct. Yes. So the question was, when I say stream processing and ordering, do I imply single-threaded? Yes. So data on a partition, I mean, you can do with it anything you want, don't get me wrong, but there is an expectation that data on a given partition on a given topic will be consumed in that order on a single thread. It doesn't matter, it doesn't matter if it's on a single thread. We can talk about, for example, reactive architectures make the ordering guarantee without necessarily guaranteeing thread affinity, but they have to be processed in that specific order. And that's really a good thing. I mean, you have other options of scaling out. And as you will see, the fact that you can have reads on like parallel reads and parallel writes make it an excellent candidate for parallelization. Right. So I was just going to start talking about Spring and how Kafka fits within the Spring landscape. And the entry point to Kafka from within the Spring landscape is Spring Integration Kafka, which is a project that has started around, I think, 2011. It was started by a colleague of ours, Sobi, I don't know. Yeah, there he is. So the main goal of Spring Integration Kafka is to adapt, basically to allow working with Kafka by using the abstractions of Spring Integration and Spring Messaging. And by Spring Messaging, I really mean the parts of Spring Integration that have been pulled into Spring Framework 4, right? Things as message and so on. Obviously, we want all that to happen without losing the unique features of Kafka. So there is, so on the Spring side, there is support for dependency injection, namespace, and so on and so forth. Some defaults in Spring Integration Kafka are, for example, more geared towards performance enhancement. So for example, by default, messages coming out of Spring Integration Kafka will not have an ID or a timestamp, which are typically pretty, you wouldn't expect it, but are pretty resource-intensive operations. So you can have that, but then it comes at a price. So the default is for you not to pay the price. The highest level of abstraction for Spring Integration Kafka are the channel adapters. So basically there are two. There is a Kafka message-driven channel adapter, and there is actually a Kafka producing method, Kafka producing message handler that actually can be wrapped into a service activator to build an outbound channel adapter. Their role is basically to, as I say, to adapt to the abstractions of the message channel in Spring and message. So anything that comes out of the channel adapter, as with any Spring Integration adapter, is a message. From there on, you don't care where it came from. You're completely agnostic as to the underlying middleware. The producer configuration basically allows for a default, like to configure a default producer, so you can set up different. You can set up the type of the key. You can set up the serializing strategy for the key and the value. They can be separate. You can have distinct configurations per topic if you want, or you can have a single generic configuration for the entire producer. The consumer actually is a bit more elaborate, so it has a few parts. It contains, so basically what we ended up doing with it was we tried using the high-level consumer, but the problem is that the high-level consumer was too limited in functionality and too buggy, and actually led to a complete rewrite of the client library. So we couldn't really wait for that rewrite to happen. It's still not production ready. I think it should be ready in about October, and we're actually pretty keen on looking at migrating to that. But we actually had to leverage the simple consumer API to do things like listening to specific partitions. So we really want an application instance to be able to target a specific partition in the topic. We want to be able to target. We want to be able to customize our offset read and write strategy, and even customize the way we actually where we actually store the offsets. One feature that came out of having our own offset management is basically that we have the ability of doing programmatic acknowledgement of Kafka messages. So I'll show you that in a second. One other things, like internally, it provides the ability of processing messages concurrently. It actually uses project reactor, so it has reactive components inside to actually allow for like really high performance concurrency. It still preserves the per partition ordering, so it's essentially like there is one ring buffer for partition group. So basically we guarantee that we don't, like even parallelizing those operations, you don't lose those, you don't lose the ordering semantics. Right, so this is an example of a consumer. You can actually point it to a bunch of, like, you can point it to a Zookeeper cluster, and then we can choose what topics do you want to consume or partitions and so on. I'll actually show you a coding example where it looks much nicer because it's done in Java config. One quick word about the message listener. So below the message channel adapter, there is a message list, basically like with any messaging project within the Spring landscape, where is it Rabbit or well, JMS for that matter, or Redis. Basically, there is a message listener abstraction that allows you to process a low-level, a wrapper basically around the Kafka original message. And this message listener can be configured in two ways. Either as like auto with auto acknowledging, which means that once an invocation to the listener has been successful, we automatically update the current offset for reading. Or you can run in manual acknowledging mode. So if you want, if the processing of your message is for any reason concurrent, then you receive a handle that allows you to do acknowledgement later when you know that your processing has been completely successful. You don't want to lose data that you're actually storing internally. Message headers. So every Kafka, every Spring message coming out of Spring Integration Kafka is populated with information about where it came from, the topic, the original topic. So if you want to do things like correlate stuff based on topic or partition ID or anything like that, you can do it very, very easily. I touched a little bit on offset management. So essentially what we wanted to do was to be able to, as I say, so the real motivation for all this was not to rely on the default behavior of pre-082 clusters that stored offsets in Zookeeper. And that's actually a performance bottleneck. So To overcome that, we actually added this offset management strategy, offset manager called, that actually has a number of implementations. So anything that has a Spring integration metadata store can be used for that. We actually have one using a Kafka compacted topic, which is very similar to what pre-082 Kafka implementations do. And then we have a recent contribution for a Kafka 082 native implementation. So basically, you can call the offset management API in Kafka 082 and rely on that. Which, as I said, is very cool because being able to control, for example, the starting offset is a good thing when you want to replay data, for example. So it makes it very, very easy. So let me show you a little bit about the, I'm going to just run a very quick example of a producer and a consumer and show you the API very quickly. Probably we should increase the font. Is it better? Right. Let me open very quickly this demo project. This is going to become later. Okay. So this is as simple as it gets with using Kafka with Spring integration Kafka and Spring Boot. This is a Spring Boot application. We're actually using this pretty nice integration flow from Spring integration DSL. So really, all it comes down to is saying, I'm creating an outbound channel adapter with a producer that actually writes to this particular, to a topic that's configured, that can be passed on. It writes strings, like the key and the payload are string. It uses the string serializer and connects to localhost 9092. That's the list of brokers that it connects to. And that's all. And when I run this application, it will just send a simple message to this particular, like to the channel adapter. And one thing you can do, actually, and this is kind of redundant in terms of a configuration, is that, for example, we can override the default setting of the producer. So even if the producer uses a specific topic as a default, you can actually provide a topic header, and then it will write to that particular topic. Let me just go to my Kafka cluster. Okay. So we have this. Let's make a topic. It can rely on automatically creating topics because that's what the producer API does, but that way you don't get the ability of targeting multiple partitions. So. Okay. I'm going to create a topic with 5 partitions and replication factor of 1. And here, I'm going to I'm going to write to this particular topic. And what I'm going to do is I'm going to configure a client. I'm going to use the console client because no, sorry, wrong project. So we should be IntelliJ not passing the right value. Anyway, I'm just going to send it to that particular topic. Yeah. Yeah, anyway. So essentially just configuring the producer and passing the message to it, it's just gets the message on that particular topic. And the consumer configuration is quite similar. So if I configure the consumer to listen to the same topic right now, and we'll receive the two messages that I sent. So you can see hold on, let me just increase the font a little bit here. If you see at the bottom, let me just see if I can actually pull it up a little bit. So at the bottom you see the message essentially being read from the topic, and with all the headers pre-populated. To be honest, the Spring integration Kafka demo itself doesn't get any more spectacular than that. It's definitely a very, very powerful. It's definitely a very powerful integration and tool. But actually, we can do even more sophisticated things with Kafka within the Spring landscape. So I'd like to introduce next Spring XD, which is actually our stream data processing platform with both support for stream and batch processing. We're going to focus on stream processing in this talk. So essentially what its mission is to provide higher abstractions around data processing. It provides means to integrate seamlessly and transparently with the middleware. It provides, it basically builds on top of Spring integration and Spring batch. And what it does, it allows really to tie together a number of, so it really ties together the existing integrations within the Spring portfolio into a structured data processing pipeline. So it relies on concepts like a source and a processor, a source that actually produces data, a processor that transforms data, and a sink that actually we can actually use for writing data, and you can chain a number of such modules together. You can already see Kafka here in both the source and as both the source and the sink. So essentially, you can connect, you can read data from a topic and basically process it in like basically pull it in your stream and process it like that. You've probably heard of Spring. Like if you see, Spring XD essentially is going to evolve into Spring Cloud Data Flow next, and Spring Cloud Stream. But the same concepts, like high-level concepts, will still remain, right? Some things are very valuable, such as the stream DSL of Spring XD, right? It allows you, like the pipe syntax, it allows you to chain things together. So for example, you can have an HTTP source piping data to a transformer, piping data to HDFS. Of course, that brings the next question, which is, fine, where is Kafka into this picture, apart from being able to have a source in the sink? Well, the message bus abstraction of Spring XD actually allows you to build a data processing pipeline by using Kafka as a transport in a transparent fashion. So wherever you see pipe into like in the syntax, that basically means that it's a hop over the transport. It means that transparently we'll get a channel, an inbound channel adapter and an outbound channel adapter wherever necessary, and those are created automatically for you, right? Other things that happen inside the bus are serialization, right? And the implementations were local, Rabbit, Redis, and Kafka, Spring XD. In terms of a runtime, Spring XD has is structured around a distributed runtime with a system of containers maintained by Zookeeper. I'm mentioning that now because even if it's an architecture that will be, and you will actually see why we are thinking to migrate towards the cloud platforms providing the same type of support. But the salient point is that this allows disjoint, like multiple module instances even, to run in parallel and to talk through the data transport. So essentially, how does Kafka comes in? It's each pipe between modules is a topic, the topics, like Kafka topics, are created automatically and managed by Spring XD. They are partitioned based on the module count in your stream. So you will see actually a stream with multiple modules, and you see the topics that are created between these modules. Also, over-partitioning is available as an option. So you can, for example, create a stream and say, well, I really want 10 partitions instead of 3 that would be normally created because I want to scale later, or just because I want to take advantage of the distribution that Kafka does in the broker for that type of thing. Multiple consumer modules. So if you have, for example, like what you've seen, for example, is the like I can have an HTTP HDFS stream, for example, with 2 HDFS sync instances, right? And each of them will get subdivision of the partition set of a topic. And because the algorithm is essentially deterministic, we can actually tell what partition goes to what module instance, right? There is, like, being able to run multiple modules concurrently and being able to essentially distribute work between them is okay, but there is another aspect that you have to take into account, that if you are doing any stateful processing, then you want correlated data to be processed on the same node. And this is where partitioning comes into play. Like, we really, really want to be able to make sure that if we're processing sensor information, we want to make sure that we process data from the same sensor on the same, like in the same node. Think of averaging. I don't want to have like a time window average for a sensor value computed on 2 separate nodes. It makes no sense, right? So here is essentially the partitioning is a combination of the partitioning logic and partitioning abstraction that Spring XD provides. So it has each stream can have a partition key expression, and it's basically the ability of Kafka to actually partition the topics. So there is a strong correlation between, for example, the partitioning, like basically the way partitioning works in Spring XD is that the expression is evaluated and hashed against the number of target partitions. And that number of target partitions is exactly the number of partitions in Kafka. So again, we're using the underlying partitioning support in Kafka to implement Spring XD partitioning when Kafka is used as a bus. And again, that's a very, very strong, very strong match for us as when doing stream processing. In terms of performance, obviously, we want to make sure that the abstraction, actually we've done some measurements. We've found that really, like in the simplest case, right? Like we took the Kafka benchmarks that have been published into Jay Krebs' blog some time back, and we tried to reproduce the same type of experiments, comparing the two. And what we found out was that, indeed, XD itself implements all these abstractions on top of Kafka with very little overhead. Of course, the numbers are very high. Once you, like the benchmarks themselves, neither the, let's say, the official benchmarks and our benchmarks do processing internally. So we have to deal with that. But even comparing like bare bones to bare bones, there is a very, very strong match between the results. So that's a good thing. And what I'm going to show you very quickly about this stream processing is kind of a more complex structure involving not only Kafka, but actually the scenario that we have is processing data from multiple sensors using RxJava and Kafka. So we've written this demo for a webinar, a few months back, and while we were actually looking at this, we found a very, very nice correlation between the requirements for high volume and low latency that Kafka provides, the functional programming model, for example, of RxJava, and the ability of Spring XD to behave as a distributed runtime. So what I'm going to do next is I'm going to start a Spring XD cluster, and let me just stop this. I'm going to start a Spring XD cluster, and I'm gonna, let me see, I had right, okay. So, okay. So first I'll need to start HSQLDB. This is already running. I'm going to create one admin node. I already have an admin node running. Okay. Right. I know where it's coming from. Okay. This is from another demo I want to show you. So our processing stream will consist of an HTTP source that receives requests. And let me just open the project. Two processors. One is calculating the average temperature over a specific time window. And the other one is basically tallying the results and displaying the top 3 sensors. Right? So this is a type of problem that lends itself very well to distributing and partitioning. We assume that calculating the average is a very expensive operation. So the averaging, like we will scale out the averaging sensors over multiple instances. We will partition that stream so that one averaging sensor receives data for all the odd numbered sensors, and the other one will receive data for the even numbered sensors. And then we will send the data to another processor that basically just calculates the top n sensors by number. So this is an example of an average calculator. You see, this is, how many of you have used RxJava or have been in a reactive programming talk at this Spring XD? So what we like about it is that it's, if you see, it lends itself very, very well to describing transformations through operators. So it has this time windowing operator that really, if I want to gather, like basically what it says is gather all data that has been produced within the last X seconds, and just create a stream with it. So it really emit separate streams of data that can be further. So what we do further is basically we group that data by sensor ID, and we calculate the average. And everything here is essentially described as a functional transformation. So it might be a little bit awkward in the beginning because it's not necessarily, if you're more used to the imperative programming model, it is a little bit backwards, but on the other hand, it's very expressive when you think of it as data transformation and in data transformation terms. Right. The other sensor is quite similar. I think I won't open that one. I will just launch the stream, basically. So I have two containers now, and what I'm going to do is I'm going to start the shell. Connect it to the stream, and I'm going to create the stream. So here is the stream definition. Right. So I've already built and installed the modules as in Spring XD, so they're custom modules. But see let me just scale this up a little bit. This is essentially the stream definition over here. So it's really a sequence of two transformers, an HTTP source, and a log sink. And for deploying them, I'm going to deploy them partitioned. So what I'm going to say is deploy this stream and set it up in such a way that I have two instances of the temperature calculator, and then the HTTP producer sends data partitioned by sensor ID. So what's sensor ID? I have this very small application that actually emits fake sensor data. Right? And what it does, it's basically emitting sensor data with a bias. What I want is to make this kind of deterministic. So the higher the sensors with so basically each sensor has, here it is. Let me just stop this for a second. It emits JSON documents that look like this: sensor ID, temperature, sensor ID, temperature. And there is a very strong bias towards the higher valued sensors. So what I'm expecting is that the averages for the sensors yes, sorry. I emitted values for a single sensor instead of 10. So let's see. Here it is. Let me just see. Data flows in. Okay. Let's just. You see, it kind of gets what I'm expecting. Sensors 9, 8, and 7 have the highest values because they're the sensors that get, like, for which the generative values are the highest. Of course, that is pretty interesting, but I like to see that everything is actually really, partitioned. So what I'm going to do is I'm going to create another container. That will display data collected of a specific topic of the data collected from the intermediate topic between the HTTP source and the average calculator, right? And I'm going to listen only to partition 0 to see what happens. So the way I'm doing that is I'm going to create this. So I'm going to be here in the shell. I'm going to deploy it. And I'm going to target a specific container. Okay. Yeah. So I should see this. Yes, that's a bug actually. Right, okay. Sorry, so basically you can see that this stream, I intentionally tried to deploy it on a separate container so that it doesn't mix up data with the main calculator stream. Okay, so let me stop this for a second. If you see, all the, like what this container displays is essentially displays sensor data only for sensors with even numbers. Why does that happen? Basically because I told it to listen only to the only to partition 0 of the topic that is used by the other stream to pass data between modules. So this kind of proves that partitioning in fact works. So I could try something else. I could try, for example, partition 1, and that should basically display even data. So you see, this is like when I changed the listen partition to 1, I'm actually getting the even numbered sensor values. Let me just, sorry, it's hard to tell. So there's that. this is basically one of the, I mean, this is a demo that is kind of telling for the ability of Spring XD1 to create partitioned, distributed streams for data processing, right? But, and this is an interesting thing, what we thought about what can we do and how can we move further on these ends, it became really, really apparent that the architecture can improve, that we actually can do far, far better in terms of how we structure the application. So some concepts are very, very valuable, essentially. The abstract bus, the abstraction around, let's say, the DSL, right? The notion of a stream and the descriptions and everything like that. What it was really less apparent was that we kind of needed a different, we needed an architecture that kind of fit better with the modern requirement, the more modern requires for scaling and basically for coping with a cloud infrastructure. Why? The key for scaling up, essentially, with stream processing is parallelism. The more you can parallelize your operations, the more you increase your throughput, the more you reduce your latency, in a way. And parallelism basically comes with its own problems. Like, not necessarily, I'm not talking about parallel programming. I'm just talking about the whole requirement to manage an infrastructure, right? Do you want to do it? Well, a single machine can actually get its resources exhausted really fast. So we're talking about CPU, we're talking about memory, right? We're talking about disk consumption, we're talking about network and saturating the interfaces, right? So one of the things that we've discovered is that it's really not, I wouldn't say hard, but it's really like trying to maintain a fleet of containers all by yourself, right, was less desirable, really. So you can buy, for example, more expensive machines and run of them, but costs are exponential there. So a number of small commodity instances cost as much as a large machine. A large, let's say, trying to launch on these separate instances is basically something more like herding cats, really, when you try to maintain a really, really large cluster. So what's the best solution for that? I mean, we could definitely go on and kind of try to push the limits of the runtime that we had, or we could try a redesign of the entire solution. So we decided to focus a little bit more and somehow change different parts of the architecture so that, and this is basically what led to the split towards Spring Cloud Stream and Spring Cloud Data Flow, right? And again, the most valuable features should be preserved, but we need to be more adapted to the new architecture. And essentially, I think you've seen the rationale for that. I mean, Mark and Dev Sire yesterday, Mark Fisher and Patrick Peralta this morning have explained very, very well the reasons for that, right? In summary, we've always thought of modules as independent units of work, as independent units, but they couldn't be launched independently. You have to take them to the container. That having a container with all classes led to all kinds of class loading issues. So we'd prefer to have each module have its own class loader and run completely standalone. And quite frankly, there is a strong desire and there's a strong, to understand, there is a very strong call towards, for example, using boot as the base for your applications. So what if instead of taking the module to the container, we actually take the container to the module? and we basically move some of the containers features and make them available to standalone applications, and then add the ability to orchestrate them. And that was quintessential. That was the essence of moving from the structure of XD with the admin container, the modules, and then the containers as runtimes, and essentially saying, well, we're going to have Spring Cloud Data Flow that does the orchestration. We're going to have Spring Cloud Stream modules and Spring Cloud Task modules that provide the programming model. And we're going to have Spring Cloud Stream and Spring Cloud, we're going to have Spring Cloud Stream module and Spring Cloud Task modules as reference implementations, as out-of-the-box modules for your tasks. This is the change. So as I said, instead of taking the module to the container, we do the container to the module. So right now, basically the binders and everything are essentially embedded inside each application. And then they are accessible through a set of programming constructs. So if you look at the structure of a module, it's become much more transparent. So essentially, you have interfaces declaring channels that your module, that your application is going to communicate on, and essentially those channels will be created and bound through this enable binding annotation. This is what it does. It's basically saying create and connect to the transport and expose that as a channel to the user. That is true dependency injection. And it's basically a much nicer model than it was before, where you had to create your own channels and then we would connect them. And it's actually much more permissive in a way, because obviously this is taken from, so Spring Cloud Data Flow, for example, has a more opinionated view of the world with the stream structure where you have sources with outputs, processors with inputs and outputs, and sinks with inputs. But this model is applicable in general to any kind of messaging application. So you don't really care. It doesn't have to be a module in the Spring XD module sense. It's just something that connects to the transport, right? So where is Kafka in this story, right? Because we are still at the Kafka presentation. Well, Kafka has basically been Kafka is kind of obviated. A great deal of effort has actually gone into providing the abstractions that allow you to not to think about the infrastructure, right? So if you have the Kafka binder on the class path, and adding it on the class path is as simple as just including it in your project, you will get, as I said, the bindings and the channel adapters and the actual channels created transparently. You can provide properties that bind those channels to the topics, right? And essentially, the implementation underneath is the Spring XD 1.x Kafka message bus. It also has support for partitioning. There is a bit of a twist, as we say here, in the sense that at Spring Cloud Stream level, we rely on partitioning information being provided to each instance. So you have to know I am instance 0 out of 7 to know what exactly you have to consume. A project like Spring Cloud Data Flow can actually do that very, very easily. And then that leads to another discussion. If we have if we have a microservice development model, right? If we have the ability to actually launch large number of instances, right? If you want to scale up in this context, right? What is the best what is the best strategy for us for going to deploy all these things? Do you want to create independent containers, or do you want to rely on some infrastructure that actually does that for us? And if you look at the stream definition here, basically what it says, I want to create a stream that just pipes data from HTTP to a log. It could be HDFS for that matter. And I want 7 instances of that log to be available, right? And I want that to happen in a Kafka cluster that also has a number of brokers and has replication, for example, between 4 partitions, right? I mean, if you count very quickly, you end up with, I don't know, 7, 8, I'm assuming there are 5 brokers, 13 instances that I have to manage just for a very, very simple stream in the world. Imagine what would happen if I would say I want to have 20 processors and 30 sensor and 30 HTTP endpoints because I have a ton of sensors that send data and I want to scale that out. So the model where you actually go and create instances and create and so forth didn't work, and we're actually relying on using the cloud to do the provisioning and to create the runtime that actually allows to execute all these instances. We deal with just writing the very simple code for these modules and the very simple statements to launch them. And what I'd like to show you is basically exactly the stream deployed locally. Actually, I'm not going to do a deployment directly in Cloud Foundry because it takes a bit long. But essentially, I have just this, running in Cloud Foundry. So let me just get to Pez. Need to single sign on. So I have a number of applications that I've tried, but the ones that I'm interested in here. So I have, well, what I'm showing you is like the Kafka tile is not available as a tile, which is a, so there is a Kafka tile within Cloud Foundry, but it's in development and not publicly accessible. So, but the opportunity exists, so it's kind of a preview in a certain sense. But I mean, we'd love to be able to provide that. It just shows how powerful the cloud's architecture is, because essentially, if you look at the, let's see, if I look at the service instance. So I'm trying to show you the Kafka instance, and to basically show you that it has so it's really a cluster of 5 nodes running since of 3 Kafka nodes and basically 3 Zookeeper instances. And I can just, like, imagine that you would have to launch that as opposed to just creating it and attaching it to your applications, right? And yeah, so I actually have 7 instances running. I had 7 instances running, actually. And we have the app server. We have actually the admin node. So what I'm going to do is just connect to the admin and connect the shell to the admin and show the stream. Right. Actually, no. Right. So this connects basically to the cloud instance of the admin node running there. And I can list the streams. And the network is not the best, unfortunately. So anyway, try that a bit later. What I wanted to show you really is local deployment with, like the last thing is local deployment with Lattice. So I have Lattice running locally, right? And basically, the nice thing of Lattice is that it allows you to do a lot of things that you would normally do with a larger scale infrastructure, but in a smaller environment. So if you don't need the whole multi-tenancy and the whole identity management schemes of Prevalent Cloud Foundry or so on, Lattice is actually quite powerful in managing multiple instances of things, so of applications, which is exactly what we want to do here. So what I'm going to do is I'm just going to start the admin node. Normally it runs in Lattice, but I have some local changes, so I will have my local machine deploying on Lattice, which also runs on my machine. So what I'm going to do is I'm going to connect to the right, because I already had an instance running from this example. The old XD and Spring Cloud Dataflow were listening on the same port. Okay, let me just stop this. Close all of that. And what this also does is, if you follow the discussion earlier about the module launcher that we use for Lattice and Cloud Foundry essentially downloads an artifact based on its Maven coordinates. So what I did was I rebuilt our standard modules using Kafka. So when was saying that it doesn't get as more complicated than this is what I meant, really. Like, instead, you just have to add this string cloud stream binder Kafka to your application, and that does it. Like, that really enables the whole enable module functionality to work with Kafka. So, for example, here's an example of an HTTP source, right? It just writes to the channels. I mean, one of the nice things about the having an interface is that you don't have to rely on channel names. You can actually do things like, well, this one in particular doesn't use it, but I could do things like channels, which is of source type, and get channels output. And I have type safe access to the channels that are created by the infrastructure. Anyway, back to Lattice. This has started. So what I'm going to do is I'm going to launch a partition stream with 3 instances. I don't dare to 7 because I don't have that much memory on my machine, so it's definitely more challenging. Now creates and deploy a partition. So this has started deployments. It's going to take a bit of time. What happens behind the scenes is that so Lattice will start basically spawning instances. And actually I can even see the log. Like, you can see the log, for example. Actually, this was a running command. So I can see the aggregated log of all 3 log instances that receive data in a single, like, just using this LTC logs partition log. And actually, that's pretty important. Like, imagine that when we run really in separate containers, we would have to go to each log and kind of look at them independently and try to figure out what happened where. You see and here is the power of, more or less, the power of cloud deployment, and even with streams, is that I didn't have to worry about starting containers. I didn't have to worry about doing anything. I could have started a stream with 10 modules and then 20 instances of each before I crashed my machine for not having enough memory. But the command itself just spawns as many instances I need and accounts for the resources. And one of the nice things that we will want to do eventually is to have support for requesting different types of resources. So you could say things like, I want, because that's another one of the strengths of cloud infrastructure, is that it can be deployed over a heterogeneous set of resources, and you can ask for different types of instances. I can ask, for example, for an instance with like high CPU for average calculation, or I can ask for more memory for an instance that does that caches reference data. So I have this freedom of actually going and assembling things together, which are not possible with a custom architecture. So let me just go very quickly and send some data, just for fun. So basically, you can see each of these applications receiving data. So I can send, I will send numbers because they're easier to track. And if you see, the same value is always received by the same instance, right? Which kind of proves my point that the stream is actually really partitioned. So in essence, this is pretty much the point that I was trying to make with this talk, which was that if you want to build high performance, high volume, high throughput data messaging pipelines, obviously you need to care about the middleware. I mean, there are things that you can do with Kafka, for example, that you can do with, I don't know, ActiveMQ, like just certain message rates that you can get, right? So that's relevant. But on top of that, you need the programming model that allows you to take advantage of that into a very transparent fashion. You need the abstractions that allow you to create, like you take the primitives that basically the transport and the programming model give you and tie them together into like, let's say, a more coherent, higher level application, like we did with the distributed stream. Like the distributed stream, essentially, when you break it down, it comes down to, I don't know how many channel adapters and how many service activators and I don't know how many things, but when I think of it, I don't think of it as such. I think it as the average processor, the HTTP source, the HTTP sink, whatever, right? And then adopting a microservice architecture for deployment makes it possible to create applications that run easily standalone. Like what I haven't shown you, for example, is that the log sync and the HTTP source and basically each and every sync and source from our ecosystem can run as an independent Spring Boot app, and I can just configure it. It's been shown a few times, so that's why I didn't insist too much about it. But you can run it. Like you can just start it, and it really behaves like the HTTP source. And the last point, I think, is once you've got to that type of architecture, when you start thinking of your components as microservices, then the migration to cloud is very easy. Like the notion that instead of running your own containers and deploying and everything, you can actually outsource all of that to an existing infrastructure that handles finding the appropriate instance to run your module on. Like there's auctioning, for example, taking place behind the scenes to ensure that the distribution is actually not like that applications, for example, do not compete on resources on a single node, right? And that basically happens at that happens at a very large scale, for example, with PCF. But one of the goals is to actually get the same thing done in not necessarily for smaller environments, but for environments that do not have the requirements such as multi-tenancy and so on. And we actually plan using Lattice for it. And you have seen that it's actually very, very easy to go and deploy to Lattice. That's the point that I was trying to make. So, I mean, that's pretty much it from me today. Stay connected, tell your friends, fill your reviews, and help us make things better. And if you're interested in Kafka, don't forget about the talk tomorrow morning at 10:30 with Joe Stein. Thank you.